Okay, yeah. Good afternoon, everyone. I don't know how many people are there in the room, but yeah, I'm happy to see that we are back to in-person meetings. Although in my case also I couldn't join in person this time, but I also want to thank the organizers for the invitation still to present our work. So today I will talk about this vortex dynamics on superconducting and non-superconducting peeling arrays. So this was work done mostly during the PhD work of Victor Royano, who's now a postdoc at INMA in Zaragoza, and this is all the rest of the people that are involved in this work, but particularly has been done in a group of José Luis Vicente together in INDEA, Nanociencia, and the Universidad Complutense de Madrid. So as you know, there are actually quite some literature on the use of periodic pinning potentials to study vortex dynamics and vortex physics in superconductors. And in general, there are like either these nanostructures, these periodic arrays are made of metal, so non-superconducting material, or magnetic materials. But in this particular case, in our case, we want to focus on the use of a periodic pinning potential generated by superconducting nanostructures. And there has been some previous work on this topic as such. So this is work from Werner Hilains some time ago, where they have looked into this array of lead rings that are deposited on top of aluminium, superconducting aluminium, and they see that these rings can act as magnetic actually pinning centers due to the flux that is trapped within the rings. And then later on, there is this work from the group of Irina Grigorieva, where they have looked now at the vortex structures in nanopillars of niobium on a niobium film. So basically it's a niobium film that is carved with these pillars. And they see here that due to this increase of the length or the thickness of the films in the pillars, this creates an anti-pinning potential for the vortices in this structure. So then later on, more close, let's say, to now, there are these two works that I want to mention where they have people have studied the arrays of vanadium dots on a niobium film, and the opposite case of niobium dots on a vanadium film. So this is the idea is to change field. So you have either, like in this case, the transition temperature of the periodic array that is lower than the hybrid system, and there they've seen also some anti-pinning effects in the case of magnetic fields that are where the vanadium dots are superconducting. While in this other case, where the critical temperature of the superconducting array is larger than the hybrid, they've seen some enhancement of the pinning actually in these superconducting hybrid structures at low temperatures, and they have also reported commensurability effects, right? So these peaks in the magnetization at when you have matching fields. So in our case, we want to study actually the effects on vortex dynamics of a superconducting periodic array with properties that are similar actually to the superconducting matrix. So for this, we chose to have a periodic array of superconducting nanostructures with a critical temperature that is only slightly larger than the superconducting matrix. And we have chosen array sites, so these nanostructures with saturation number so that they can allocate more than one vortex, right? So the saturation number is larger than one, and actually they will form an asymmetric pinning potential. So in practice, this is what we have done. So it's basically an array of, in this case, niobium triangles, monotriangles, so with lateral dimension of the order of 600 nanometers. And then on top of that, we deposited a film, a vanadium film, right, of 100 nanometers. We have also what we call a witness sample, so a reference sample, where now the array of triangles made of copper. So it's a non-superconducting material, so we can have that to contrast our results and to be sure what are the effects of the superconductivity. So in this array, there are some important numbers. One is the matching field, in this case is 39 Erste, so that's the field, as you know, where we have one vortex per triangle, in this case, per pinning site, and the dimensions are such that This saturation number, so the number of vortices that can be allocated in principle in the triangles, is larger than 1 and actually is similar to the interstitial saturation number. So if you look, so the triangles are indicated here with these blue lines, and if you look at the interstitial lattice that is formed, is this down red triangles, right, that they have similar size as the physical triangles. So this is completely or very different, let's say, that the previous case where actually the matching field was much larger, so 0.2000 Ørsted, and the nanostructure was in this case made by using an alumina layer. So the separation between these dots, so these were like also niobium dots on a vanadium sample, or a vanadium film, are much closer, and there is the interstitial space, let's say, is much smaller, and the array is not perfectly periodic. Okay, so what we did first was to look at the matching effect, so this magnetoresistance curves as a function of temperature. So as we lower the temperature, we start to see these minima in the resistance that increase, of course, the further you go down in temperature. But the interesting thing here is that we don't see, so if you see here, we have normalized by the matching field, so we don't see a minimum resistance at the first matching field, right? And this is, of course, consistent when we look at the critical current as a function of field, and we don't see this enhancement that is usually observed at the first matching field. So to understand this, so what we did, if you look now, we take one of those curves, this is 0.97 of Tc, and we look close to field equals 0. So our argument here is to say, well, at the first matching field, the niobium triangles that are already in the superconducting state, they repel vortices, so the vortices will sit at the interstitial sites between the triangles, and therefore this causes a weak clipping vortex lattice. Now, when we increase the magnetic field, so that we have the second or the third matching field, there will be more vortices there at the interstitial sites, and this causes what is called the gauging effect. So the vortices again are a better pin, and there is a pin enhancement at these matching fields. So this is more clear now when we compare these magnetoresistance curves for similar temperatures, when now the pinning potential or this nanostructured array is made of normal metal. So this is the case of the red curve, that is the vanadium copper hybrid structure. So where you can see clearly, of course, the minimum at the first matching field and the second and third, of course, and that the intensity of this minima actually is much more similar between the different fields, while this is not the case for the superconducting nanostructure. Okay, so the next thing that we did was to look into the vortex dynamics in this system. So here we have, just to compare, IV curves done in this vanadium niobium hybrid structure, and also the vanadium copper hybrid structures. And well, from here we can determine, as usual, the critical current in these two systems, and this is what is plotted here. So we see that this niobium periodic array of triangle generates a much less efficient pinning potential for the vortices. So we see a lower or a decrease of the critical current compared to the case of this vanadium copper hybrid. These are the examples for the first and the third matching field, where we see that consistently for different fields. So the other thing that we looked into from the IV curves is, so the IV response also gives information of the vortex structures. So as you know, what we did here is to do the derivative of the IV curves as a function of current, and then we see that at higher temperatures there is a divergence of this derivative, while at lower temperatures there is this maximum that moves with current. And this has been associated previously with this change, let's say, in concavity of the curves is associated with this liquid to glass-like phase transition. So that also is consistent when we do this scaling of the resistivity with temperature with proper parameters, and we see that this the curves, let's say, the scale on the liquid phase altogether, while on the solid phase, they're also overlapping. And then the transition temperature determined like this is similar to what we get from this analysis of the derivative of the IV curves. So when we do this analysis for both hybrid systems, we see that actually, so this now is the HT phase diagram. So we plot the temperature as a function of field. It's normalized in this case again by the matching field. So this is the HC2 line, of course. And then what we see is that for the vanadium niobium hybrid system, this glass transition temperature is much lower than compared to the case of the vanadium copper hybrid system. So this indicates, so this lowering of the transition glass temperature indicates that there is a weaker vortex-vortex interaction in the system. So to try to understand that, we went back to some previous results on arrays of magnetic dots, where a larger critical current here was observed also for the case of interstitial vortices. So this is permalloy dots on niobium film, and when you compare the critical current of the permalloy dots, again as a function of field, is larger than the case of copper. So the argument here was to say that due to the stray field of this permalloy, of these magnetic dots, there is a decrease of the effective penetration length, and therefore that decrease in the penetration length causes a stronger vortex-vortex interaction. So in our case now, we we argue that now something the opposite, let's say, if you want, happens in this case. So now we have these superconducting triangles, actually, but areas here, and that induce due to the screening currents that are circulating in these niobium triangles, that causes an increase in the effective lambda, and therefore a weaker vortex-vortex interaction in this system, and that can explain this lowering of the glass transition temperature. So to finalize, the one thing that the other thing that we look into is let's say the magnetotransport now in this high temperature region of more like the vortex liquid phase compared to the case of the low temperature case. And what we see is that at high temperatures, the matching features in the magnetoresistance are very clear, and actually there is also reversible behavior when we sweep up or down the magnetic field. While when we go to lower temperatures, to the region where the critical current is different than zero, we see that these matching features are less pronounced, and actually there is also an hysteresis between the going up and going down magnetic field. And this, again, is consistent with the fact that there can be now flux trapped in the superconducting triangles, so in these niobium triangles, that can cause this hysteresis at low temperatures and actually larger fields. So this is observed only for fields larger than the third matching field. So with all this, I just want to summarize our results. So just to say that I think I clearly show that we observe an anomalous matching effect at the first matching field that is caused by these superconducting niobium triangles, and that's due to the fact that the vortices sit at these interstitial sites that are between the triangles. We observe also a significant decrease of the critical current and the glass transition temperature, possibly due to an increase of effective lambda in these hybrid structures. And finally, that at low temperatures, we observe an absence of matching features and an appearance of an hysteresis of the magnetoresistance. So with this, I just want to acknowledge, well, these are the approaches that support our research, and I want to thank you all for your attention.